This is Mr. Smith with the Academy for Allied Health. We're getting into the chapter on circular motion and gravity. Some simple vocabulary we want to look at. First word is axis. Axis is the line about which circular motion occurs. Rotation means that the axis is within the object, so the object itself is spinning. Revolution means the axis is outside the object, so it's going around something. The object is going around something. It's not the object itself that's spinning. Okay, so real world, Earth. The Earth rotates on its axis. This is why we have night and day. We're on the side when it rotates away from the sun. We have nighttime when the sun is on the same side, or we're on the same side as the sun, is really how it should be. We have day. And it revolves around the sun. And because it's tilted on its axis, that's why we have seasons. So, if you have a spinning circle with a radius of r, you can figure out and get this nice little equation where delta S is the arc length, delta theta is the angular displacement in radians, and of course r is the radius. What is a radian? A radian is an angle subtended by an arc that is the same length as the circle's radius. What does that mean? Basically, this is not 100% accurate, but basically you're making an equilateral triangle. So you're taking your radius and you're putting the three segments of the radius together, in a sense, trying to form a triangle. Remember, the whole idea of doing these and looking at this in this area of physics is that we're going to solve physics with Pythagoras. Pythagorean theorem and a little trigonometry. Okay, we're not going into the calculus that bases all of these. Okay, if we were, then I wouldn't be trying to con you into thinking that this is an equilateral triangle. But there's a radian. The distance that goes is 1 radian. Now, of course, it takes 2 pi or 6.28 radians to make 1 revolution. That is, for it to go in 1 complete circle. So, that means 2 pi radians is 360 degrees and pi radians is 180 degrees. So, how do we work this out? Well, in a Ferris wheel, remember, a Ferris wheel driver, he's got the people getting into the Ferris wheel, and then that moves, and the people who are in the basket get out, and the other people get in, and then that one moves, and boom, boom, boom. So going from basket to basket, the arc length, the arc for the baskets is 3.8 meters. What we want is the angular displacement. Okay, so let's get our equation for arc length. Turn it around so we deal with, or move it, maneuver it, so that we are dealing with angular displacement. Our arc length is 3.8. Our radius is at 11.5. So that's where the basket is. That means we've gone 0.33 radians. That's the angular displacement. Okay, so next question is, for the inner circle, what's the arc length between these stops? So the inner circle is going to move the same angular displacement. Only now we're dealing with a radius of 7.5 meters. So what's the arc length on the smaller one? It's less. It's 2.5 meters. Same radius, same angular displacement, smaller arc length. Okay? That's going to become important when we get into Kepler's laws. It's also why gravitation is included in this chapter. Hopefully you'll see more of that, and that will get revealed to you as we move on. All right. If your Ferris wheel is rotating at constant angular speed, it takes 18 seconds to go around once. We want the average angular velocity. Now, in first dimensional kinematics, when we did this, average velocity is displacement over time, right? Well, it's the same kind of thing in angular velocity, only we call it the angular velocity being the angular displacement over time. Using that, what's our angular displacement? 2 pi. And so our angular velocity is 0.35 radians per second. The Ferris wheel takes 2.2 seconds to go from rest to its average angular velocity. What's its angular acceleration? Okay, again, we were doing first degree motion. We remember that acceleration is velocity over time. In angular velocity, the angular acceleration is angular velocity over time, or in angular motion, I should say, right? So we want to solve for angular acceleration. Our angular velocity is going from 0 was the initial, and it went up to 0.35 radians per second in 2.2 seconds. Therefore, it has an acceleration of 0.16 radians per second squared. Let's now use this for something that we all need to really be thinking about, because this is what's going to get us into the idea of gravity. This movement bends space. The idea of angular movement is something that should be fundamental to us because it's actually what's happening to us on the planet. Okay? So we're going to do this. We're going to find the angular velocity of Earth. First, spinning on its axis. Remember, Earth is doing two things. It's spinning on its own axis, so we're moving. And remember, we're moving so that our place where we are comes back into sunlight every 24 hours. Okay? So it completes one spin every 24 hours. But it's also revolving around the sun. So let's see what we're talking about with angular velocities. All right, so angular velocity is angular displacement over time. Again, right, it goes one whole complete circle, which is 2 pi rads in a day, which is 6.28 rads in a day, approximately. We put that in where we do our conversions. Day is 24 hours, an hour is 3,600 seconds. Everything cancels. And we get 7.3 times 10 to the minus 5 radians per second. To revolve around the sun, the angular speed, again, this time it takes a year to go 2 pi radians. So I imagine that you are going to find this angular velocity to be much less. And it will be. 2.0 times 10 to the minus 7 radians per second. Okay, great. That doesn't help us. You know why? Because I really can't relate radians. So, before I get into how I can get into a real speed, something that's a bit more tangible for us, something we can understand, something we really see. I don't know about you, I don't spend an awful lot of time watching circles move and figuring out their radial speeds. Let's do some comparison of what we've had so far with our angular velocity and angular motion equations. Okay? In linear and first dimensional motion, average velocity is displacement over time. In angular, its angular velocity is the angular displacement over time. In first dimensional motion, average acceleration is velocity over time. Same thing here. Average angular acceleration is the angular velocity over time. You can find displacement in one-dimensional motion by going 1/2 a delta t squared. You can find the angular displacement by going 1/2 times the angular acceleration delta t squared. You can find a final velocity if you remember its initial velocity squared plus 2 times the acceleration times change distance. You can find the final angular velocity if you have an initial angular velocity plus 2 times acceleration, angular acceleration, times angular displacement. You can also find displacement as 1/2 of the sum of your two velocities, delta t, okay, which also can be done the same thing with angular. There's an extra one for angular motion though, and that is arc length. Arc length is angular displacement times the radius. We call it the 6-man. Now, what are the conventions? Okay, that means positive and negative. All right, well, going counterclockwise is positive. Okay, that's why it's 0 at the east, 90 is north, 180 is west, 270 is south. Clockwise direction, everything increases, that's what's positive. Negative is going in the, or counterclockwise direction. Negative is going in the clockwise direction. So heading down to 270, that would be what? Negative 90, negative 180, then north would be negative 270. You get my drift. Why? Where do these conventions come from? The right-hand rule. Blame it on the fact that there's a majority of right-handed people. All right, let's try to figure out a problem. A car is rotating at 52 radians per second. It's going to brake for 7.3 seconds. The wheel will come to a stop. Let us find the wheel's average angular acceleration. Okay, so we use the change of angular velocity, which of course, since one of those is 0, that makes it real easy. Initially it's 52, so it's a negative 52. So of course it's negative acceleration. Why? Because it's actually decelerating. However, the angular displacement is heading not in the reverse direction, but remember the tire is still going to keep moving in the direction it was. It's just going to come to 0. So instead of using the negative angular acceleration, we're going to make it the absolute value in a sense. And when we feed that in, we find that the angular displacement is 190 rads. So it's going to complete quite a few revolutions. Okay? Tangential acceleration. That's where we really get to look at meters per second and we understand where things are. Tangential acceleration is the radius times the angular acceleration, which means, of course, angular velocity has to be changing. It can't be constant velocity. So let's try one. Bike wheel goes from 5.8 radians per second to 9.3 radians per second over 15 seconds. We want the tangent acceleration for the reflector and the valve stem. We've got the radius of both the reflector and the valve stem. So let's see what we get. We are going to get two different numbers. Okay? Remember, tangential acceleration is radius times the angular acceleration. Angular acceleration is also the change of angular velocity over time. That's what we have in the problem. So we change angular acceleration, in a sense. We make the adjustment so we can carry out the math with what we have. And we get 0.096 meters per second squared for the valve stem at 41 meters radius. For the reflector, its radius is less, 0.32. We use all the other same numbers, and we're going to get an acceleration of 0.075 meters per second squared. So it's not going to take off as fast. So after 15 seconds, what's going to be the tangential speed? Now we need velocities. Okay, same situations. For the valve stem, tangential velocity is radius times angular velocity. So we get 3.8 meters per second. For the reflector, we get 3 meters per second. So let's try this with our Earth and Sun. The Earth and Sun distance is 1.5. Excuse me. The distance between the Earth and the Sun is 1.5 times 10 to the 11 meters. Let's find the linear speed around the Sun in meters per second. That means we need tangential velocity. In this case, tangential velocity is 2 pi r over the period. Well, what's the period? Period is a year. Okay? Make our conversions to seconds. And we get about 30,000 meters per second. Which, if I do a conversion for miles, is 19 miles a second. That's pretty fast. The town of Normal, Illinois sits at longitude 40.5 degrees north, or latitude, 40.5 degrees north, which is about where we sit. What's the tangential speed of normal around the Earth's axis? First thing we have to do is resolve the radius, because obviously normal is not that far from the axis as the equator. So it's a little less, 4.89 times 10 to the 6 meters. We use that in our tangential velocity equation. Again, 86,400 seconds. That is what it takes for normal to go around once. Right? It's one night, one day. 355 meters per second. Centripetal acceleration is acceleration toward the center. It is part of what causes what we know as gravity. It's not everything with gravity, but it's a big part of gravity. So for a circular motion, tangential acceleration may be 0 or non-zero. However, centripetal acceleration is always non-zero. It is equal to the tangential velocity squared divided by the radius, or the radius times the angular velocity squared. Two ways to find it. Let's find the resultant now, or the net acceleration of the moon. Since tangential acceleration and centripetal acceleration are perpendicular component vectors of the net acceleration, we can add them like any two vectors. Now, what do we know though? We know that tangential acceleration for the moon is 0. It's not drifting off away from us. It's staying in its orbit. So there is no tangential acceleration. Therefore, the resultant equals the centripetal acceleration, which is a very minute 2.3 times 10 to the minus 3 meters per second squared. The moon is ever slowly heading back towards us. It was originally a part of us. It's heading ever slowly towards us. Then we're actually heading ever slowly towards that. We are falling towards each other, but we never touch. What would be the tangential velocity? Wait, there's no acceleration. How can there be a velocity? Remember, velocity, if there's constant velocity, so we consider the tangential velocity to be constant for the moon, which is why acceleration is 0. Remember how those graphs work? In first dimensional motion, they work the same for circular motion. So centripetal acceleration is tangential velocity squared over the radius, shifted about, plug in our numbers, and we get 940 meters per second, tangent to the EM radius, Earth-Moon radius. So let's see what the force that the Earth has pulling on the moon. Let's use the mass of the moon. Remember, the total forces are mass times acceleration. So that also means that it's the centripetal force. So there's a number of different ways to figure out centripetal force. We could have mass times centripetal acceleration, which of course could also be mass times tangential velocity squared over the radius, or it can be mass times the radius times the angular velocity squared. So we'll use the first one since we have those numbers. Plug them in. And the force is about 1.7 times 10 to the 20th newtons towards the Earth. Which is why it won't leave orbit. Let's see where you can also use this. 2.6 kilogram stone is at the end of a 0.74 meter rope, and it's twirled horizontally at a constant rate. The period for this is 1.1 seconds. What's the tension on the rope? Okay, well, the tension is a centripetal force, right? The period is 1.1 seconds. Tension is centripetal force. Centripetal force, mass times the radius times the angular velocity. Angular velocity is completion of a spin. How long? Is 1.1 seconds. Squared, you get 63 newtons. Now, where do we use circular motion all the time? We use it a lot in physics in dealing with roller coasters. So at the bottom of a loop with a radius of 16 meters on a roller coaster car, travels at 13 meters per second. Let's find the force of the track on the car. Okay? The force is the track pushing on the car, not the car pushing on the track. Actually, what do we say? It's not really in the air, it's on the track, right? So they're equal and opposite. That's why you feel at different parts in the loop, you can feel weightless or you can feel pressure. And that's because it's equal and opposite. So let's see what it is at the bottom. At the bottom, right? Because you know at the bottom of the loop, that's where you suddenly feel heavy, right? Like you're being forced down into the seat. Well, what's going on? Well, you've got a centripetal force and you have the normal force counteracting the weight of the car, or mg. So the force of the track is the normal force plus the centripetal force. So we'll put those two together. Force of the track is, of course, or normal force is, of course, mg. We can equate that. And remember, one of the ways to find centripetal force is mass times tangential velocity squared over r. Put those in, and you get 5.1 times 10 to the third, 5,100 newtons. That's why it feels so heavy. Now, what about that force, right? Isn't I being pushed into the car? That's not happening. We call that centrifugal force. It doesn't exist. It's apparent. Why is it happening? Because space is being bent. It exists only in a local reference frame. It is an effect of inertia. You feel it. You feel space bending around you. So consider a ride where you're spun, one of those where you stand up. Okay? From your frame of reference, what do you see? You feel that you are pushing yourself into the pads. There's something pushing you in. But there's nothing there. So what could be pushing you? What's actually happening, if you were able to look from the top, from an aerial view, is you would see pads pushing on you, changing your motion. Okay, and because your motion's being changed, how do you feel that? And how does that get reacted physically? The space around you is changing. What do? You feel that force. Now, the magnitude of what you feel actually matches the magnitude of the centripetal force that's existing. Remember, third law, your body is giving an equal and opposite reaction to what's happening. Okay? So, for example, you're on the school bus. Student is on the bus is moving 15 meters per second. It's going around a curve with a radius of 16 meters. Student starts to feel pressed against the window. What is this centrifugal force that the student suddenly thinks is happening? Well, we know that that's not it. It's the centripetal force. We know the centripetal force is mass. We just did it, right? Times tangential velocity squared over the radius. Plug things in. Centripetal force, 770 newtons. Let's look at the space stations. One of the things, we're going to start talking about gravity in the next section. So let's talk about gravity and circular motion. Part of circular motion, again, like I said, can create the gravity. So let's think about it. If we had the space station has an 8-meter radius, 16 meters in diameter. We wondered if we were able to set it spinning, what rate must it spin so that the people inside now feel that they have a gravitational pull and would be actually able to do things like it could do them on Earth. That's something that we would like to do. Certainly if we're going to put man in space long term, we need to be able to simulate gravity. We don't want weightlessness. If we don't, we're all floating around. We don't want to have that situation. It would definitely hurt us. So we've got to watch our spin, because if the spin is too large, well, then we'd end up being flattened against the sides of the space station. We don't want that. On the other hand, if it's too short, it's not going to keep us there. But what we want to find is that ideal spin that'll keep us upright. So let's do some comparisons. We need a force on the person and the Earth's gravity. So force on the person is obviously the centripetal force. Okay, we have that figured out. Earth's gravity is mg. Let's equate the two. That way we get rid of masses. Therefore, we can find that angular velocity, or the spin, is gravity over radius, square root. Plug in our number. We get 1.1 radians per second. That means the period for it to complete one revolution, it would complete one revolution in 5.7 seconds. Okay? So let's find G at eye level if the average person's height is 1.7. Let's just figure this out. Okay, so now instead of having an 8 meter radius, we have a 6.3 meter radius because we're at the eyes. That means the centripetal force, or the G, is 7.6 meters per second squared. There's a problem. What's the problem? Well, the body can't handle a head to foot difference in G of only 1%. Anything more than 1%, you can't deal with it. Okay? So at eye level, G is 7.6. At the feet, it's 9.1. This isn't going to work. 8 meters won't work. So let's see what we can do. Again, let's look at weight. Right? We had centripetal force. So let's take these equations and equate them all. Okay, on both sides. What does that mean? We get rid of our masses. And in this case, G for both is RW squared, or R angular velocity squared. We want the angular velocity for both to be the same. Okay? Angular velocity is going to be the same. So, if this is the case, in circular motion for a constant angular velocity, see, angular velocity is going to be constant for our case. That means that G only depends on R. So centripetal force only depends on R, or acceleration. Okay? So what does that mean? Well, since the radius at the feet is greater than the radius at the earth, or greatest radius at the eyes, I should say, then the force of gravity at the feet will be greater than the force of gravity at the eyes. So, therefore, if the forces are going to be different, or the gravitational acceleration is going to be a 1% difference, then that means, based on our equations up top, the radii can't be more than 1% difference. So since a person has a height of 2 meters, average, that means that we have to have a radius where 1% is 2 meters. Which means our minimum radius for our space station, if we're going to simulate Earth's gravity up there, is 200 meters. So it's 400 meters in diameter at least. That's big. 200 meters, that's like 6 football fields end to end. More than that, a little more. Quite a lot. All right? But as we can see, we can get into gravity. Now let's see how that works. That'll be our next section. Talk to you there.